Our context is the growing interest in the standardization of processing pipelines for multimodal image that is focused on structural and functional features that are a more complete and precise characterization of all brain states. This is specifically with the inclusion of high temporal resolution techniques like MEG and EEG that will allow to determine the functional parameters in the cortical space. Another requirement is surface-based processing of the source models, lead fields, and activity and connectivity, because this places attention on cortical architecture to obtain precisely the cortical multimodal features. This strategy must be adopted also for all imaging modalities, and including MEG and EEG. We are appointed to fulfill robustness, replicability, but this is somewhat challenging for data acquired with different standards, equipment, formats, and protocols that is calling legacy data. The Human Connectome project has introduced requirements as well as protocols for imaging MEG and EEG, but ACP methods are not robust for badly conditioned lead fields, which are common in legacy MEG and EEG. Then robust methods must be introduced. We have introduced the BC-VARETA pipeline that includes novel methods for MEG and EEG source analysis of the activity and connectivity in the spectral domain, following ACP standards. Inside BC-VARETA, mathematical sparsity priors control directly distortions of source spectral variances and covariances. This is unlike classical methods like LORETA and LCMB that have been implemented inside the ACP pipelines. We have also introduced surface-based structural sparsity priors based on ACP-like structural processing into BC-VARETA. This reduces the bias to sparsity and provides cortical anatomical information to the mathematical priors, such as cortex surface neighbors, depth compensation by curvature, rotational invariance for fields, and parcellation smoothing. This has been tested in large databases, producing consistent results for MEG and EEG.